Donc nous avons le grand plaisir aujourd'hui d'accueillir David Wineland pour le séminaire du jour. Je vais passer à l'anglais pour qu'il comprenne un peu ce que je vais dire. So we are very pleased to welcome today Dave Wineland. We're going to give this seminar on single atom clocks. I think everybody knows Dave Wineland. He has made his PhD studies with Norman Ramsey back in the 1960s, and then he went for a postdoc with Hans Dehmelt in Seattle, where he made very important work on the single electron system, which led to the measurement of the G-2 factor of the electron. And then he moved to the National Bureau of Standards, now called NIST, where he has been doing, during the last 30 or more years, very beautiful work on ions in traps. So he's really the world specialist of trapped ions, using them for quantum information purposes, and also to develop very precise atomic clocks. And in fact, the clocks he will be talking about today are the most precise in the world. It's really astonishing the kind of precision you can reach now in the measurement of time. So I won't spend much more time. I want to thank Dave because he accepted to come to give this talk and to cross the Atlantic at a time where he has a lot of traveling to do, as you might imagine. So I am very grateful that Dave made this effort. I want to add that we have been knowing each other for more than 20 years, and it's always a pleasure to welcome him in Paris or to go and visit him in Boulder. And I'm very glad to give him now his microphone. So, Dave Wineland.
Let's see, Serge, the lights. Okay. Well, thank you very much, Serge, and it's a pleasure to be here. I think by now you all know that Serge and I have done very complementary work for which we were recognized this last year, and but I'm not going to talk so much about the experiments on quantum state manipulation, or rather maybe just focus on one aspect of that, which is the idea of making atomic clocks. And so just to summarize, I'll give some very basics about clocks and a little bit of history of why we use atoms. In particular, I'm going to talk primarily about using trapped ions for atomic clocks, and I understand from Serge that later in this lecture series that you'll have a talk on atomic clocks with neutral atoms in a lecture by Sebastian Bies. So I won't talk very little about that work, but you'll get the picture of what's being done with neutral atoms from Sebastian. In particular, I'm going to focus on single atoms, and the short story is that with single atoms we can most precisely understand the systematic effects, and that's why we think about using single atoms, or in the future groups of single atoms. And I'll talk a little bit about where we hope to go in the future. So I think everybody intuitively knows how a clock works. We have some periodic event generator and some counter, which then allows us to generate time. And of course, historically, the most precise clocks were based either on the rotation of the Earth, or more in the last century then pendulum clocks. But of course, there's some particular advantages of using atoms, and we can either think of a classical orbit of an electron around an atom, which is very closely approximated in the experiments of Serge, but more generally we think about some oscillating wave function, which has typically an electric dipole moment. But in any case, we can think about it's simple to think about an orbiting electron. Of course, we know from quantum physics that an equivalent picture is that is that if we have two energy levels in an atom, the frequency at which the radiation drives this transition with maximum probability is given then by through Planck's constant. The energy separation is the frequency times Planck's constant. So why do we choose atoms? And just there's many reasons, but I'll give you some idea of the advantages of atoms. And for example, I'll compare to a classical pendulum clock. I think we all know how a pendulum clock works. And so one of the things we have to worry about is frequency shifts of our standard, whether it's a pendulum clock or an atom. To give some idea there, for the pendulum clock, of course, it depends on temperature because typically the length of the pendulum will change with respect to temperature, given by the thermal expansion coefficient. And just to give a rough idea, a good low thermal expansion material has a thermal expansion coefficient of about 10 to the minus 8, and what that results in, just following what the pendulum equation gives us, that the frequency shift is about a little under a part in 10 to the 8th per degree C then for a material with that expansion coefficient. So with atoms, say we consider atoms confined in some sort of box here, and just very simply we'll assume the box is not perturbing, the bounces off the walls of the box is not perturbing the atoms. One thing, the thing we have to worry about, and we have to worry about in the most advanced clocks, is the effect of relativistic time dilation, the fact that the atoms are moving, time moves slower for them, and we have to account for this effect. Well, it can be a fairly, if we think about if we characterize the motion of the atoms through, if they're in thermal equilibrium, we can easily calculate this effect. Of course, it's given by this expression here, the so-called second-order Doppler relativistic time dilation effect. And we end up with, so fractional shift is given by this expression here. And just, for example, if we had cesium atoms, the fractional shift per degree temperature change is about a part in 10 to the 15th, so it's dramatically lower than the temperature effect of a pendulum clock. So that's certainly, obviously, one advantage to using atoms. The other has to do with reproducibility. Of course, just from the simple expression for the frequency of a pendulum clock, it depends on both the length and also the local gravitational acceleration. Of course, also another effect in practice you have to worry about is that pendulum clocks wear out. There's friction in the system, and they can change due to wear. With an atom, of course, the really nice thing is that all atoms of a particular species are, as far as we know, exactly identical. So there's no problem with reproducibility. And of course, atoms are such simple mechanical systems, and we know they never change, they never wear out, so we don't have to worry about that effect either. So to make an atomic clock, the prescription is extremely simple. We have let's suppose we have some cell of atoms, cell that holds our atoms, and one way to make an atomic clock is we have some radiation source here, an oscillator that produces radiation, and basically we'll have some simple servo mechanism that allows us to stabilize the frequency of the radiation so that we absorb on the resonance of the transition, meaning that the transition probability is maximum when the frequency of this oscillator is tuned to resonance. And then we simply count cycles of the oscillator to produce time. In a little more practical way, what we typically tend to do is, rather than synchronizing to looking for the maximum of the transition probability, what we typically do is given in this cartoon here, showing a classical atomic beam resonance spectrometer. And what we think about is, if we, let's say we have some state preparation mechanism that initializes the atoms in typically the lower state, and then we send it through this resonance cavity. This is this resonant cavity here is split into two parts, where the atoms first pass through this first zone, which ideally has the fields have the same phase on both ends of this special cavity. In the Ramsey method, I'll say a little bit more about that in a minute here, but basically this first zone excites the atom processes freely then in this drift zone, and then we probe the atom again with the same fields to change the state. And then finally we measure the state. What an example I show here, which is maybe the more modern version, is to use optical pumping with lasers and then state-dependent fluorescence to detect the final state. In the traditional machines, this state preparation and detection was done with a Stern-Gerlach magnet, but so the lasers are a refinement on that, but the basic idea is just the same. And so actually, although it may be a little bit more complicated in practice, the simplest way to stabilize to the center of this resonance feature is we typically probe on one side of this resonance feature and then the other, and basically what our servo does is just to make the response on the left side be the same as the response on the right side. And when we have that condition, assuming the resonance is symmetric, which is a good approximation, very good approximation, then we know when this response is the same, then the mean of the frequencies on the left and right side is equal to the resonance frequency. So that's basically what we do to detect the center of the resonance, and it's really not much more complicated than that. Now, with this in the atomic beam resonance apparatus, the resolution of this feature, the line width, is basically closely proportional to 1 over the observation time. That is the time it takes to traverse this free precession zone. To give one example, actually this was when I was first at the NIST, the National Bureau of Standards. The cesium clock at that time was based on this more traditional atomic beam apparatus, and in that case it had a length. This free interaction length was about close to 4 meters, which gave a resolution on this hyperfine transition of about 9 gigahertz of around 30 hertz. So more modern application of this same basic idea is the atomic fountain, and of course these fountains exist in primary standards labs throughout the world now. I show the example of the one here down the street at the CERT research lab, and this atomic fountain was the application towards this realization of the second was first realized by this group here. But in any case, one of the main advantages of this of the fountain is that the atoms move very slow, and basically by launching the atoms vertically, they can go up and come down, and the interaction time can be on the order of a second, which then gives a resolution of a little less than 1 hertz. Another nice side feature of this is that the atoms go up and come down through the same cavity. So we know that to a very high degree, the relative phase when they first go through the cavity is the same as when they come down and then are detected. So in a little more detail, let's suppose we think to simplify the situation, let's suppose we're dealing with n atoms, and could be n atoms in some given time that go through the beam apparatus or the atomic fountain. And in the case of atomic ions or trapped neutral atoms, we think about a fixed number of atoms that are held in one place. In any case, the typical situation in this Ramsey spectroscopy is that we start out, let's say, with all the atoms in the ground state. We have some, in this case, the state is separable, so it's basically just an ensemble of individual atoms. And we start the atoms, and I'll typically use the label of the down arrow, meaning like an analogy with a spin 1/2 particle, the spin down or spin up. In any case, we start with the atoms in the ground state. In the Ramsey method, typically the first so-called Ramsey pulse will put each atom in an equal superposition of spin down and spin up. And then during the time they evolve between the pulses, the atoms, of course, freely process at their frequency, but if the radiation is applied at some frequency that's slightly different, then there'll be a phase difference between the evolution of the atoms and the radiation pulse that supplies the second pulse in the Ramsey method. So it turns out if we then measure the average number of atoms that, say, end up in the excited state under this condition, then the probability of the atom being in the excited state is then just given by this simple expression here. And of course, we see sinusoidal fringes given by this expression here. Now, in fact, the fringes repeat. They continue to repeat, and by a simple bootstrapping process, we can know which fringe we're on. And then typically, as I said before, we'll have some central feature, and we typically probe the response on this side of the fringe, and then on this side of the fringe, and we balance the response on those, and then the mean frequency is at this resonance frequency. Interesting in this case, if we could precisely count the number of atoms without errors, then again, just essentially this expression here, where I've represented the phase by the frequency difference between the atoms and the oscillator times the time between the Ramsey pulses. In any case, ideally then we get a signal like this, where on resonance then the atoms are completely promoted to the excited state after these two pulses, and at some detuning given by this expression here of pi over 2, then the atoms are put back in the ground state, and we see these 100% contrast fringes. In this idealized case, then the signal, we get the most sensitivity, of course, when we're on the slope of this transition here, so that the signal, we might say, is the change in the response versus the frequency detuning, or this phase, and that's given by this simple expression here. Now, what the noise in the system in this idealized case is given by the fact that when we have an ensemble of atoms, and particularly when we're on the side of this fringe here, that means the final state before measurement is an equal superposition in the ground and the excited state. So for each atom, we know from quantum mechanics that the probability of the atom being in the ground excited state is 1/2, and there's also fluctuations on that. So what this expression represents down here is basically the square root of the variance of the measurements we get on all of these n atoms, and it's basically just the fluctuations are given by the binomial distribution, and we end up with this expression here where this represents the probability of being excited to the spin-up state. And in this idealized case, then the noise in this experiment is just given by this simple expression here. And in fact, the signal to noise then is just given by the square root of the number of atoms that we're probing. Interestingly here, what that means is that if we can realize this idealized case, it doesn't matter where we probe on this line. We could be up very near the top of this resonance. We still get the same signal to noise. What the statement there is that even though the signal goes down the slope, the fluctuations also go down proportionally. So in this idealized situation, it doesn't matter where we probe on the feature. But of course, if there's any added noise, and there always is, then the place where we really want to be is where the signal is maximum. So we typically probe on the side of the lines. Anyway, let's. Although and that's not always true, but it's just to set a common stage for how we think about doing the spectroscopy on atomic clocks. Let's assume the Ramsey method. It can either be through time of flight, as in the atomic beam apparatus, or in the fountain. When we trap atoms, we typically just think about in the time domain, where we apply 2 Ramsey pulses simply separated in time to the atoms located in one place. Let's carry through this idealized case. Let's suppose that we're using the Ramsey method, and the noise is this so-called projection noise, which I didn't label it that but this fundamental noise that's due to the probability of the atoms being detected in one state or the other. And it turns out in this Ramsey method, assuming this idealized case, we get a very simple expression here where the statistical uncertainty in our measurements is given by this expression here. And not surprisingly, it goes down with the square root of the number of atoms. It goes down with the square root of the averaging time, and this T sub r is the time between the application of the Ramsey pulses. And it also goes as 1 over the frequency. Anyway, this is what we want to keep in mind as we think about how to optimize the performance of a clock. And of course, what I've represented here is the statistical uncertainty in the measurements. But there's 2 things we want to keep in mind. We want small statistical uncertainty, which is typically called the stability, but what we really mean is the instability in our measurements. That's what's important. But we also want to keep in mind the systematic frequency shifts, and so it's these 2 things. We want to strike a balance between those because we know we need those both to be extremely small. So as I mentioned at the start, I'm going to mainly focus on trapped ions, and Sebastian Wies later will talk about related experiments on neutral atoms. Of course, the problems we face, there's a lot of commonality in the problems that we face, and with some differences. And I'll mainly highlight the issues with trapped ions. So a little bit of history here. Actually, when I was a graduate student, I was, as Serge has said, I was a student with Norman Ramsey, learning about atomic clocks. In that case, it was the hydrogen maser and related projects. At that time, I was also reading about the experiments of Hans Dehmelt, and he was doing some very nice experiments measuring helium-3 hyperfine structure. with ions in a so-called radio frequency or Paul trap. And in any case, at that time, the systematic uncertainties in the experiment were about a part in 10 to the 9th in these experiments. Later, there was a simpler or a more practical ion to look at. This was a microwave hyperfine transition in mercury, which had the advantages. It was quite a bit higher frequency, and also I won't describe the pumping and detection mechanism in these early experiments by Hans Stamel were very complicated and actually a tour de force to be able to do these measurements. In these later experiments the first ones were done by Fuad Major and Gunther Wert. They were able to use basically optical pumping and detection by more traditional means by using a mercury isotope, different mercury isotope, the radiation from that to be able to do the pumping and detection. They were also able to get down to systematic frequency shift of about a part in 10 to the 9. And both of these experiments were limited by the fact that in the case of ions, what happens is if we have a collection of ions, what happens is they by the mutual Coulomb repulsion, even if we if we can cool the thermal motion of the ions down, the Coulomb repulsion holds them apart, basically space charge. So what happens I'm not going to take time to describe all the features of this pseudo-potential Paul trap, but basically the trapping works because ions are confined in an inhomogeneous RF electric field. And it's important that the fields are inhomogeneous when averaged over an oscillation period of this RF signal. On average, the ions feel a force that pushes them back towards the center of the trap. But out here near the edge of this cloud of ions, the ions are undergoing what we call micromotion. It's basically the motion in these RF fields. And in these experiments, then, one of the issues was that the main limitation on the accuracy was the uncertainty in the so-called second-order Doppler time dilation shift, due to the fact that the ions were jiggling back and forth in these electric fields. And as I say, for a large sample, the space charge would hold some of the ions out here on the edge, and they would be subject to this so-called RF micromotion and the frequency shift due to the time dilation. So one way, at least, to try to get around this problem of this so-called micromotion is a lot of us tend to use what we call linear pseudopotential trap, and this is based, if you're familiar, might be familiar, this is basically a quadrupole mass filter where we make a trap out of it by applying positive potential. For a positive ion, we apply positive potential on these end segments to hold the cloud of ions near the axis. Now, the reason this is interesting is for this linear quadrupole structure, as opposed to this more spherical geometry, which I showed in the last view graph. Along the axis of this system, the RF electric fields are zero. So if we can make an elongated sample of ions that confine the atoms near the axis, then we suppress this effect due to the ions oscillating in these applied electric fields. Actually, there was a lot of work has been done on this over the years. I think in this case, using this hyperfine transition to make a clock, John Prestige and his colleagues at Jet Propulsion Lab have done the most work. their goal is to try to make a stable clock that will work on a satellite, and because of that, they've restricted themselves to not use the lasers just for simplicity. They use, again, this optical pumping with using a resonance lamp for a different isotope of mercury. In any case, they get down to where by confining the atoms closer to the axis of this trap, they get down to a systematic uncertainty of about 2 parts in 10 to the 13. More what they're interested in is the stability, and they can get down to stability or instability of about 4 parts in 10 to the 16 per day. In some of the experiments we did, and I'm only going to mention these, we also looked at this 40 gigahertz hyperfine transition in mercury. In that case, using lasers to do laser cooling, we could basically put a string of ions along the axis of this trap and highly suppress the second-order Doppler shift due to the motion in these external electric fields. And so we could reach an accuracy, a systematic uncertainty of about 4 parts in 10 to the 15. The big difference between these experiments and what John Presage at JPL does is simply that we had this 194 nanometer laser beam which could do the laser cooling and also do the optical pumping and state detection. In this case, just to give an idea, here we went to, even though we typically had on the order of 5 to 10 ions in this experiment, so it wasn't a single ion experiment, but just a few ions, and the way we could get a reasonable stability was that we went to very long Ramsey times to offset the fact that we had a small number of ions, and we typically in this experiment went out to 100-second probe times to be able to reach these precisions in a reasonable amount of time. So one other thing, again, this is a long-winded way of trying to tell you why we went to single ions rather than a group of ions. And one of the reasons, or one of the primary ones, is that we also in mercury, it has an optical transition which potentially was interesting, and so at about 10 to the 15th hertz rather than 40 gigahertz, and it had a fairly narrow line width given by limited by the radiation lifetime of the upper state, which is about 1/10 of a second. And the reason for going to high frequency, if I'm rewriting this or showing this same expression again, the statistical uncertainty basically goes down linearly with frequency. So one crude way to say why we win is at the higher oscillation frequencies, we just divide time up into finer and finer pieces because the period of the oscillation has become smaller and smaller. So that was the main reason. I mean, we knew about this for a very long time, that it'd be good to go to high frequency, mainly because we win linearly with the frequency. The biggest problem then with why we want to go to single ion, it turns out that if we just had 2 mercury ions in the trap, for the typical parameters, the electric fields, the inhomogeneous electric fields from one ion on the other ion interact with the quadrupole moment of this D level and give a shift, and the typical magnitude of the shift is on the order of a kilohertz, which is fairly high. Now, of course, you can argue, well, you can quantize the atoms along a certain direction where it nulls this shift, but there's fluctuations. Also, the problem, the problem or the issue that's more of a real practical problem is there end up to be contact potentials of varying degrees on these electrodes. So we end up with some stray inhomogeneous field when it interacts with this quadrupole moment, which causes an uncertain shift due to this on this upper D level. So anyway, this was a long-winded way of saying why we think about going down to single ions. In this case, if we go down to 1 ion, then we get rid of this 1 kilohertz shift due to adjacent ions in the trap. And so even though we think about, I'll talk mainly about 1 ions, of course, one way we're going to lose in signal to noise if we're here with just n equal 1 versus n equals some large number. We're going to lose because of that. But so in the end, we think about maybe making ensembles of single ion traps. But anyway, I'll stick with a single ion for the purpose of the discussion. And I would say when Sebastian Bies gives his talk, this is where the neutral atoms can win substantially, because for typical conditions, they can talk about trapping a much larger number of atoms for example, in optical lattices. Okay, so coming back again, why, again, I'm going to make this point, well, it'd be nice to have very large frequencies and also get very long interaction times. When I was a student with Norman Ramsey, Robert Pound, who was also a professor at Harvard, he was famous for working on precision spectroscopy using the Mossbauer transition. So he used to tease us, well, if you want high frequency, why not go to a Mossbauer transition? And one example he posed was that it was a particular transition, actually, it's silver, yeah, and that has this energy here, so a resonance frequency of about 10 to the 19th hertz. It has a lifetime of about 58 seconds, so in principle, the Q of this transition can be really dramatic. And of course, the answer of why we don't think about such systems is, first of all, we need in general, when we go to high frequency, we need a stable local oscillator, the oscillator that probes the transition. Now, in Mossbauer spectroscopy, the way it's done typically is we have there'll be one sample that radiates, and the radiation from that sample is imposed on some other sample, which we can observe the absorption on. And the way the frequency is detuned to the oscillator is just to move the atoms, use the first order Doppler effect. So in some sense, we have the oscillator in those experiments. But the real killer, if we want to make a clock out of these, is how do we count cycles of the radiation? And this remains a extremely impractical problem right now. And another little side note here. So if we go to optical transitions, this is not a new idea, and to point that out, this is something actually that was found in this, discussed in this article here. But basically, this idea of using atoms for, in this case, optical clocks goes back at least to this period here, and this is a text written by Lord Kelvin and his colleague Tate, who talked about. They attributed this idea to Maxwell, and basically what Maxwell proposed was using the oscillation, and he mentions the sodium particle, and what they're thinking about here is the optical oscillations of the electrons in sodium. Of course, they didn't really understand relativity then, so this statement here is not exactly right. But this idea, I find this interesting because the idea using optical transitions goes back very far compared to what we're doing now. So we starting in 1981 in our experiments in Boulder, we were thinking about mercury. I mentioned that it has this high hyperfine ground state in the high frequency hyperfine transition in the ground state. So there was interest in that, but also we knew about this transition in this optical transition, which in principle had a fairly high Q, and we were also using laser cooling to reduce the time dilation shift. And the way the experiments go then in this case is we typically think about applying this source, pardon me, the clock radiation alternately with this detection radiation. So if we prepare the atoms and the ions in the ground state, we first apply this clock radiation, and then we turn that off and then turn on the detection. The reason we alternate these is that, of course, the laser that does the cooling and detection can give a considerable stark shift to this transition here, so we don't want to perturb the resonance frequency due to this transition. That's why we alternate these back and forth. In any case, the way the detection works then as preparation of detection, we let the atom decay into the ground state. We then apply the radiation. If this radiation is off resonance, the atom remains here, and we observe this fluorescence when we apply this laser. If we promote the atom to the excited state, then when we apply this laser, the fluorescence goes away. And we see data like this where if the atom, it's basically what I said, if the atom remains in the ground state when we apply this radiation here, then we see fluorescence. If the atom's been promoted to the D level, then there's basically this is just the background light that we detect. And obviously you can see if we set a discriminator level somewhere in between, we can detect with essentially 100% efficiency when the atom makes the transition. Now, having said that, even though we have this 100% efficient detector, we're still the noise in the system, and then are these so-called fluctuations due to projection noise. That is the statistics of whether the atom actually makes the transition or not. So the two things that we need to do is as I mentioned a couple of view graphs back, let me just recall that. Oops, maybe a little farther. Maybe. Yeah, we need a stable local oscillator this oscillator provides the radiation, and we need to count. We need a way to count cycles of the oscillator. So this. In our lab, Jim Berquist and some postdocs and students he is working with, they basically, this is the standard way that everybody uses to stabilize a laser, that is to get this stable so-called local oscillator. And basically, in this case, as with other experiments, it's a simple two-mirror cavity. The idea is to what happens in a practical sense. We stabilize to the resonance of this cavity, this two-mirror cavity, and in fact, the electronics is good enough that the laser using feedback, the laser tracks the frequency of the cavity to a very high degree, and then what we're left is the fluctuations in the laser then are governed by the fact that the spacing between the mirrors is not perfect, and there's fluctuations due to that. So in the case of what Jim Berquist in our lab did, is he took a very lowbrow approach, but it was very successful. He made small optical tables, which you see are supported on these rubber bands to basically give a mechanical filter for low frequency. The finesse of the cavities was fairly high. Excuse me, and with that, he was able to, by having two of these separate systems on separate suspended tables, he was able to, he and his colleagues were able to measure a beat note between two lasers at 560 nanometers, which just represented data. This shows an average over 20 seconds and a residual line width of about 0.2 of a hertz. And although we didn't understand at that time what we now know the limits of this due to, this is the fluctuations in length of the cavity, and it turns out the basic length changes of the cavities are not due to so much to the spacer that the mirrors are mounted on, but it's actually the fluctuations in the substrate of the mirror. And all the, basically this still tends to be the limit in these cavity stabilized lasers that these days several labs have reached performance roughly equal to this. And as I say, we now know that it's primarily limited by the fluctuations in just the vibrations in the mirror substrates. So how do we count? Now in the old days, there were these heroic experiments where people would start at a low frequency, say a hydrogen maser, synchronized to a cesium clock, and basically the procedure was to do harmonic mixing, take a low frequency oscillator, multiply it up in a nonlinear element, and then compare it to some higher frequency oscillator and stabilize the phase. And then there was these complicated change. This shows an example from the group in Germany, and NIST had a similar system, and other standards labs had these systems. But obviously you can see it's extremely complicated, occupied rooms full of lasers. And I'm not going to say much about this. I understand you had a discussion from a lecture from Ted Hench a week or two ago, and I think I'm not going to even describe the story. Basically, by using these so-called self-referencing combs, it was a way to relate the optical frequencies to the rep rate of a mode lock laser with very high precision. So in a very short time, from the early work by Ted Hench and Jan Hall and their colleagues, within a very short time we could have in our laboratory this device that would do the frequency counting for us. So in our lab, as I say, we pursued mercury, and this work over the years starting in 1981 is largely due to Jim Berquist. And in any case, this is I showed on the very first view graph, this is a picture of a single mercury ion in a trap. And so just some of the features that we get in this experiment. First of all, the fact of just trapping itself, it means that on average the velocity goes to zero. The average velocity goes to zero. The atoms aren't moving. So that gets rid of first order Doppler shifts. Laser cooling helps to suppress the time dilation, the so-called second order Doppler shift. In this experiment, we also went to 4 Kelvin. What that does is it helped, for example, it freezes out a lot of the background gas, so it prevents frequency shifts or at least suppresses frequency shifts due to collisions. It also suppresses Stark shifts from the black body fields. Those go at proportional temperature to the force power. But actually, the reason we went to 4 Kelvin was that it turns out that at a room temperature apparatus with mercury, when we put some mercury vapor in the system and we make ions by typically either photoionizing or electron bombardment ionizing the ions, the neutrals to make the ions. In those experiments, that we'd always have some vapor in the background of mercury, and it turns out that the mercury, when it's in the D level, the excited state of this optical transition, if it collides with a neutral mercury atom, it can radiatively associate, make a dimer. What that means is that our ion for the clock disappears. And at room temperature, the typical situation was that this process would happen about once every 10 minutes. So every time we get everything tuned up, the ion would disappear and we'd have to start over. By going to 4 Kelvin, where we could get the high vacuums, the lifetimes literally went from 10 minutes in one case to over 6 months. So that was the main reason for going to the low temperature at that time. But anyway, after a lot of work, you see that we started in 81, but in 2006, Jim and his colleagues were eventually able to reach a systematic uncertainty of about 7 parts in 10 to the 17. And this was the first time that any clock had surpassed the systematic uncertainties of the cesium clock. Now, of course, the problem was cesium was a moving target and people were always improving it. What impresses me is the fact that even though we were able to exceed the systematic uncertainty, cesium was an amazing choice because it was, of course, the first cesium clocks were made in the mid-50s, and then the standard of cesium for the second was defined, it was adopted in the mid-60s, and it was the best clock for all this time in terms of systematics until around 2006. And I've only focused on our work at NIST, but there's several labs throughout the world working on different ion species, and I have to apologize for not giving credit to their work, except if you want to find out more about these other experiments, it's summarized in this paper by Patrick Gill. So one of the things we've been working on is quantum information, doing these state manipulation experiments. And I'll give an idea. This is a particular project in our lab where we're using aluminum ions. Aluminum ions are attractive because the excited state now has a lifetime of about 20 seconds versus a tenth of a second in the case of mercury. This project in our lab is headed up by Till Rosenband. In any case, the basic idea is the following. As with mercury, when we try to excite this transition, in principle, there's an allowed electric dipole moment in aluminum. We could use this same fluorescence detection method to tell when the aluminum ion makes a transition, a clock transition. Unfortunately, the wavelength here is uncomfortably short. Basically, it's just impractical to get a CW source at this wavelength at least at the current time. So what we do is we use a trick that one of the elements of our experiments on quantum information processing, and the basic idea. What we do is in the ion trap, which I represent by this harmonic potential, we also put another ion. In this example here, it's magnesium. And the basic idea is that if we can, in the idealized case, we freeze out the motion, we cool all the modes of this two-ion system to the ground state, and then after we excite this transition, in general there'll be the aluminum ion will be in some superposition state. And it turns out with some simple techniques that we use in quantum information, we can map the superposition state of the aluminum ion onto a superposition state of the ground and first excited state of one of these motional modes. And then we map that superposition onto the internal states of magnesium. And it turns out with magnesium, we can actually use this, again, this fluorescence method to tell which states. So we basically indirectly measure the states of aluminum by mapping them onto magnesium and then detecting them in the usual way. So what about the systematic uncertainty here? And I'm not going to be able to cover all the details, but it at least give you kind of a flavor of the things we think about. So very generally, it's not too hard to create a list. We list all the forces of nature and ask what each one does. Now, of course, the strong and the weak are short range, and they're fairly fixed on the ions, so they're kind of built in. We don't, at least till now, we don't have to worry about those. We do have to worry about the effects of gravity, and more commonly, the usual culprits are electric and magnetic fields. Electric fields can take any form. Actual electric fields from the trapping fields, or, for example, in the collision processes and things like that. There's also which I call observational shifts here, basically due to how we measure what we measure on the atom relative to our reference frame in the lab. So for magnetic fields, this is everybody in atomic physics has to worry about things like this. So we have to worry about linear shifts, say Zeeman splittings in the sublevels of these optical levels that I showed. We also have to worry about second order effects in the magnetic fields. And one of the calibrating the Zeeman shifts, we can just measure the Zeeman shifts and calibrate those out. We can measure some of these from static fields. It's easy. Once we have the Zeeman splittings, we can calculate these second order effects due to static fields. But the tricky part is how we characterize the oscillating magnetic fields. And one of the issues we have to at least consider in these ion traps, again, I apologize, I don't have time to go through all the details, but basically you put an oscillating electric potential on two of these rods in this quadrupole structure. Now, in general, there's some capacitance of these electrodes to ground, and these potentials we apply, then there are currents that flow on the electrodes. And due to imperfections in the way, just the way we construct the trap, these currents that flow on these electrodes due to these applied potentials, in general, we have to assume they're going to be different. The problem is that in the mercury experiment, these fields in the aluminum experiments, these applied potentials are at about 80 megahertz. The way we can measure, say, 60 hertz or 50 hertz here is those are at such low frequency that we can see a frequency modulation spectrum, which helps us extract the oscillating B field at 60 hertz or 50 hertz. On the other hand, at 80 megahertz, the modulation index is so small that we don't get enough sensitivity. So I mean, this is a real problem because we're kind of blind about what the AC magnetic fields at this frequency might be. But it turns out we're saved because one of the nice things in this method where we're putting a magnesium ion in with the aluminum ion is that in previous experiments, we've measured the effects of oscillating magnetic fields on the magnesium hyperfine structure. And it turns out the magnesium hyperfine structure is much more sensitive than the effect on the aluminum ions. So we have a nice way to calibrate out these second order magnetic fields due to these high frequency applied potentials. So one of the things in terms of electric fields that we have to worry about, well, first of all, one of the nice things about ions is the fact that any linear effects of electric field, they vanish simply because we know the ions are located in one place. They're not moving because, and what that means is the average electric field has to be zero then. Another thing, of course, we all have to worry about in the optical domain are black body fields. At room temperature, they're typically about on the order of 10 volts per centimeter. So we need to deal with that. Now, strategies to do that. We could cool down, as I mentioned in the mercury case, the black body field scale with at the fourth power of the temperature. So that's one fairly straightforward way to do. The other is just to measure the polarizability of the atoms or ions and control the temperature. Or we can get lucky, and that's what happened in aluminum. We didn't really realize it when we started out, but the polarizability the differential polarizability of the ground and excited state of this clock transition in aluminum is extremely small. It's the most favorable. And so in this case, we basically can work at room temperature, and we don't have to know the temperature, the local temperature very well to be able to calibrate out these stark shifts from the black body fields. One of the other things that it sounds kind of simple, but we have to worry about it. The experiments we do on aluminum right now are at room temperature. We have, even though we're at fairly high vacuum, below 10 to the minus 10 torr, we do have to worry about collisions. And one of the problems is that there's no, first of all, we don't know precisely what the background pressure is composed of. We have to, so we don't have any calibration on what collision shifts would be. And one reason we have to be careful is that one of our early experiments on laser-cooled clocks was actually, we made a clock based on a hyperfine transition and beryllium ions. And we made an estimate based on collision shifts due to in other ions. But we got a big surprise. We were off by about 2 orders of magnitude. It was 2 orders of magnitude worse. And we're not positive, but after searching the literature, what apparently can happen is that if a background gas molecule comes along, it can for a short time associate with, in this case, beryllium. When it comes, the neutral atom comes and collides with beryllium, the energy of the collision can go into the internal vibration rotation motion of this complex, the beryllium neutral atom complex, so that the neutral atom stays around for quite a while and then eventually flies apart when the energy comes back out due to this collision. So anyway, we believe that's what was happening with beryllium. Anyway, so with that lesson in mind, we had to assume that we knew nothing about the collision shifts. So what we do to establish an upper limit on collision shifts in the aluminum experiment is that what we can assume is we can assume the worst case, which is that each time we have a collision, let's assume a pi/2 phase shift on the clock oscillation. I mean, it's extremely unlikely it lands at that value, but because of this earlier lesson, we have to assume the worst case. Now, one of the nice things in this experiment, putting a magnesium ion with an aluminum ion, is that when a neutral atom collides with the atoms, these collisions are dominated by a so-called Langevin process, where basically the neutral atom is polarized by the ion. It spirals in and imparts the energy to the ion and comes back out. Anyway, since we're at room temperature, it turns out the short story is that with high probability, with 50% probability, the ions get enough energy from this Langevin collision process that the ions switch places on average about 50% of the time. And we can measure this switching of position. So that's what we use. We assume the worst case that a collision causes a pi/2 phase shift on the ion, and the collisions we see are about once every 2 minutes for a typical vacuum conditions. So we can put an upper limit on the collisions in that case. Again, we're coming back to these, what you might call observational effects. We have to worry about the Doppler shifts. The first order Doppler shift goes to 0 so that the atoms are trapped. That's actually that's a little bit too simplistic. One thing we have to worry about is if we're shooting for a fractional precision of 10 to the minus 18, then if the atoms during their probing time move with a velocity of, in this example here, about 0.3 of a nanometer per second, then we get a shift that we have to worry about. And in fact, this one thing with we have to worry about was when we turn on the lasers to probe the transition, there might be some charging effect due to the laser, could push the ions, and so we can't assume that the ions are perfectly stationary. What we actually do is we probe in 2 directions to take this effect out. We didn't really see anything substantial, but we just can't assume that they're not going to move. So we have to guard against that. The other thing we have to worry about is, of course, this is common, anybody in these experiments now, we have some laser system on part of the table and the trap is over on some other part of the table. The laser could be, say, due to thermal drifts in the system, it could be moving at some very low velocity compared to where the trap is. So we have to take out this Doppler shift, and this is a common technique when people compare lasers and do these kind of experiments. And actually, we first got the idea from ranging of satellites. Basically, you measure the Doppler shift by reflecting a signal off the distant object, either satellite or the ion trap, and we measure the Doppler shift due to that effect, and we can calibrate that out. For the second order Doppler, I've mentioned that a couple times now. Certainly the laser cooling takes out most of that, but we do have to worry about, due to residual stray electric fields in our ion traps, the ions can be pushed off their null point of these oscillating electric fields. And we do have to account for that. In fact, that's the current limit on the experiments with aluminum. So, and the other thing we have to worry about is now we have to worry about the gravitational potential redshift and the outcome of Einstein's general theory of relativity. And as a practical matter, on the surface of the Earth, if we raise if we have two clocks that are at the same vertical position in the lab, and we raise one clock by a meter, the frequency shift is a part in 10 to the 16, and so we have to worry about those effects when we compare clocks. And just to give you an idea, this is an experiment we did just for fun, so there were at the time of these experiments a couple of years ago, there were two aluminum clocks on small optical tables you see here. Obviously, this clock is not really portable, but in this experiment, we could. What you'll see here is we put some jacks under the table. So we first measured this clock relative to one in an adjacent lab that was essentially at the same height, and then James Chow here is working, as you'll see, to raise the clock. In this case, he raised it about 30 centimeters, and we could see this gravitational redshift. Obviously, it's not really an accurate measurement of the gravitational redshift, but we could see the effect. And one of the things that, of course, we knew with the answer we should get, and so we weren't surprised by this. But the unfortunate thing, what it means these days, is that in order to, if we have two clocks and we want to compare them, in a practical sense, we have to compare them in the same location, because, for example, actually Boulder is maybe a worst case scenario because of the topology, the mountains nearby. The uncertainty in the gravitational potential expressed in terms of height is only known to about 30 centimeters. So if we get down, now that we're at these high precisions, where the precision is below, certainly expressed in terms of gravitational potential redshift, is below 10 centimeters, this means that we have to compare clocks in the same location if we want to really compare their frequency accurately. So what about the future? I think there's certainly the future of the application, the primary application of clocks over centuries has been in navigation, and we never run out of. People often ask, "Well, aren't your clocks good enough now?" And the answer, which has always been true throughout history, is no. If we have better clocks, we can find new applications. If we can get clocks that, in this case, say this represents, in terms of this gravitational potential redshift, about part in 10 to the 18th. If we can get down to those precisions, we could, for example, measure Earth strains. And one thing people talk about is this might be a precursor to predict earthquakes. Of course, we can turn this whole problem around. I mentioned that we have to, if we want to compare clocks, we have to compare in the same location. We can turn that around and do geodesy, that is, measure for example, measure the geoid of the Earth, the position of constant gravitational potential. There's some fundamental tests that we've always been interested in. I haven't mentioned, but some of what's popular among the precise clock groups now is to compare transitions that depend in a different way on the fundamental constants with different strengths of the fundamental constants. And so, for example, we could do in some effect a real-time measurement of the potential time variation of a fine structure constant by measuring clocks over roughly a mercury clock versus the aluminum clock over roughly a year period. And other labs are doing similar tests. And maybe we can, if our clocks get accurate enough, we can then probe, Einstein's theory of relativity to a higher precision that's been done up to the present time. I know I'm running over, so I'll make this my last slide, but let me say some people are familiar with the idea that we could use particular entangled states. Serge talked a little bit about this at the end of his lecture. One that's interesting for clocks is the fact that if we make this particular entangled state, so it's an equal superposition of n atoms being in the ground state with an equal component in the excited state. And the interesting aspect of this state, each of the upper states has a e to the, I forgot the I here, e to the I omega naught t phase factor. And with n atoms in this particular entangled states, this upper state, it processes n times faster relative to the ground state. So it's like having a single entity, which a kind of super atom that runs at a rate that's n times faster. And it turns out that you can, if you can work with these states, you would get a statistical uncertainty, which then improves rather than as 1 over the square root of n, it comes out of the square root, and it goes as 1 over the number of atoms. And in fact, we've been able to at least demonstrate the features of these entangled states in this regard. In practice, what happens is this expression here holds if we're limited only by this projection noise that I talked about before. In practice, in the real situation, there's noise on the oscillator that probes the transition, the laser, and it typically is 1 over f noise, and we have to deal with that. And it turns out these papers discuss the case where typically then because of this noise on the laser, we lose the gain that we get from the states is counteracted by the noise in the laser, which there's really no advantage. Now there's some other, I list these references here, there's some other ways to improve using particular entangled states, but I won't go into that. Anyway, because I am running a little long, it turns out there's a way around this problem of the laser noise, but I won't describe that here. And let me just finish. I want to thank certainly my colleagues at NIST. I show the current members and recent past members. And as I say, I've focused on work at NIST, but there's many groups throughout the world doing similar and very good work on these problems. So with that, I'll conclude. Thank you.